In this chapter, chemical equilibria or chemical equilibrium, we are setting the stage for a large portion of Chem 2. So I really need you to try to understand not only the math, but conceptually what's happening here. I need you to picture these molecules, picture these pieces, these particles, these ions, whatever you're looking at in solution. I need you to picture them in their system. Picture those gas molecules, picture the liquid, picture the solid, etc. And really try to understand what's going on, because this chapter is setting us up for not only this chapter, but the next two as well, where we talk about specific types of equilibriums. This is generalized. We are going to get into specific types, but you really need to have a hard grasp here to be able to be successful at the next two chapters. I do have this broken down into smaller chunks. I hope that helps digest it a little bit better. So let's get to it. In this first chunk, per se, we're going to talk about equilibrium systems as a whole and really try to start understanding this concept of an equilibrium constant and be able to determine what this constant represents. So what is a dynamic equilibrium? A dynamic equilibrium is defined as a state in which no net change, I keep saying charge, no net change occurs because there are two opposite processes occurring at the same time. Let's pull back out of chemistry for a little bit. The first time I ever really saw this in my everyday life was shortly after COVID had hit. And my daughter and I went to Sam's Club because I desperately needed some things from Sam's. And when we got there, stores were still distancing. They were still limiting how many people could be in the store at a time. And so as we walked up to the front of the store, there was a line out front that we had to wait in, every 6 feet apart, of course, from the other people around us, because the store had reached capacity. So we're standing, here's the storefront, and here's all these little groups of people 6 feet apart waiting to go in. And there's a little employee standing here that was checking us as we went in. This employee's job was to make sure that her counter didn't go higher. I vividly remember this woman standing there with a little clicker in her hand. As customers left the store, she would allow one to come in, and we would all move up one space in line. Another customer would leave, she would allow another one to come in. And they were making sure they were staying within count. See, from a bird's eye view, if I zoomed out, if I went up in a helicopter and just looked down, and I didn't actually count the people, if I just looked at the building itself was not changing numbers. The number of people inside the building was staying constant, but the people themselves were changing. There was people coming out of the store and leaving, and there's people arriving at the store and going in. That's a dynamic equilibrium. It's this process by which the rate of the people going into the store was equal to the rate of the people coming out of the store. Now let's put this in the terms of chemicals. Let's say we have a saturated solution of sodium chloride. If I have a beaker with some sodium chloride in here. If I have sodium chloride and I dump a whole bunch of solid in here, and I actually see some solid hanging out at the bottom, not reacted, I naturally know that sodium chloride wants to split apart into sodium ions and chloride ions. But I can add so much to solution that no more will dissolve. You could do this in your own kitchen. You could take a small container, dump a bunch of salt in it, and put some water in it. At some point, you're going to have more salt than the water can actually dissolve. It's going to dissolve what it can. Let's pretend this is actually in the box because I need to be able to write these out. It's going to dissolve what it can, but it can't. Eventually, we're going to reach that saturation point, as we talked about in the solutions chapter, where no more will dissolve. And so some undissolved sodium chloride will remain. What's happening here is we have reached what we call a dynamic equilibrium. Some of that sodium chloride is breaking apart to form ions, while some of it is coming together. These two coming together to reform the original sodium chloride. And we call this an equilibrium. We specifically draw it with these arrows. These are what I call your equilibrium arrows. please note that they are specific to an equilibrium system. A double-headed arrow like this is for resonance. This is not correct either. Now, on a computer, that may be all you can get, but when you're drawing them out, you should be drawing equilibrium arrows. These equilibrium arrows show us what they represent is that we have reached this dynamic equilibrium. Sodium chloride, the sodium chloride themselves, if we have like a crystal of sodium chloride, it's splitting itself apart while it's being hydrated. Remember, salvation, if it's water specifically, we call it hydration. Those are being hydrated, forming sodium ions and chloride ions, whereas at the same exact moment and the same rate, sodium ions and chloride ions are coming together in solution to reform that solid. It's happening at the same rate, both forward and backwards directions, so we don't notice the change overall, and it has reached an equilibrium. Picture here to kind of show it as well. We see here initially, we've got the particles, nothing's been formed yet. We've got the little white pieces here, the little white diatomic represents H2, the little purple diatomic represents I2. And we're forming HI. Initially, we only have H2 and I2 present. But over time, we're going to eventually reach the equilibrium. Over time, the H2 and I2 react, and we're forming HI. We form more HI. And eventually we reach an equilibrium where the concentrations are no longer changing. So if we look at a graph here, concentration versus time, we see initially we have a certain concentration of H2 present and a certain concentration of I2 present, and we don't have any HI present. Over time, though, our concentration of I2 is decreased, our concentration of H2 is decreased, and our concentration of HI has increased. What we're talking about in this chapter, at equilibrium, is when we've reached that steady state, when the rate of the forward reaction is equal to the rate of the reverse reaction. In the kinetics chapter, we talked about the rate of a reaction, and for a kinetics chapter, we're talking about something over here. We're talking about the rate at which it's changing. At this point, nothing else is changing in the overall bird's eye view. We have reached equilibrium, and we can say the concentration of H2, that's not H2, hold on. That would be HI. The concentration of HI at equilibrium, the concentration of H2 at equilibrium, and the concentration of I2 at equilibrium. So let's draw another system ourselves. Let's talk about N2 plus H2 giving me NH3. If I react 1 mole of nitrogen, diatomic nitrogen or molecular nitrogen, with 3 moles of H2, diatomic hydrogen or molecular hydrogen, I will produce 2 moles of ammonia. This is known as the Haber process. It's a well-known, very famous process to produce ammonia. And I can talk about the reaction in either direction. Let's first talk about taking N2, reacting with H2 to form NH3. Concentration versus time. Initially, I'm starting out with no NH3, but I'm going to produce some at some rate, and it will eventually level off. When it levels off, I will have reached the equilibrium concentration of NH3. I will start with some N2 present. It will react and it will help form some NH3. But at the end of it, there will still be N2 left because it's forming an equilibrium. How much is left? It depends on the equilibrium. We're going to talk about how to determine how much is left once we reach equilibrium. But in an equilibrium system, everything, both our reactants and our product, are all present at equilibrium. It's not a reaction that's one-sided. It's not all this is reacted and produced this. It's everything The reactants and the product or products are present once we reach equilibrium. And for H2, I'm going to draw H2 up here just because I know I have 3 times as much H2 as N2. And it's going to decrease and then reach some sort of equilibrium state. Now, is it higher than NH3 or lower? I don't actually know. I have to do the math on it to figure out where it actually lies. But once we reach this steady state, this is equilibrium. All 3 species are present, and that's what we're studying in this chapter. Up here, when they're still changing concentration, this is your kinetics. We can also look at this going the other direction. So let's say we had 2 moles of NH3 reacting to give me 1 mole of N2 and 3 moles of H2. Because it's in equilibrium, the reaction can go either direction. If I started out with just ammonia, it will produce N2 and H2. How much? I don't know. I would have to calculate it, but it will produce it. So initially, I'm starting out with no H2 until I reach some equilibrium state. I'm starting out with no N2. I know I have less N2 than H2 at equilibrium just because it's a 3-to-1 ratio, but I don't know how much exactly. And I know I'm starting out with NH3 actually present, and it's reacting, and I will have less of it once I reach equilibrium. So again, over here, after time has passed and the equilibrium has been reached, this is what this chapter is looking at. And up here was the kinetics chapter that we covered. So there are 2 characteristics of chemical equilibria. We have 2 processes, 2 opposing processes. This should say changes or processes, but we're going to take out that word. Keep forgetting to delete that. 2 opposing processes that occur at the same rate, but they are opposing. They're doing the opposite thing. They're opposite of one another. But because they're happening at the same rate, bird's eye view, we don't see the difference. Number 2, at equilibrium, the concentrations of reactants and products do not change with time. Again, that's because of the processes occurring at the same rate. Things are changing, yes, but bird's eye view, nothing is changing. So how does this factor into an equilibrium constant? We have Kc and Kp, and truthfully, we're going to find a lot of Ks. Kc is for concentration, Kp is for pressure. And we're going to talk about both in this chapter. We're also going to learn how to convert between the 2. So Kc, C representing the concentration of X in moles per liter, so your molarity. Kp, where P represents the pressure in atmospheres. We call this equation your Kc equation or your equilibrium constant equation, expression. It's also known as the law of mass action. You're going to hear all of these terms with this. But what I want you to realize here is what we've done. To find Kc, I call this your products over reactants equation. That's not quite correct because it's leaving out information. But when I think about it, I think of products over reactants. Now, you have to be careful with that. There are caveats to that. But if I remember products over reactants, it's a ratio. How much product do I have to how much reactant do I have? It gives me an idea where the equilibrium lies, and it also helps me remember how to calculate the equation. So the way we do this, products over reactants, you take your product, and you're going to take whatever species you're looking at, and you're going to determine the concentration of that species. The coefficient on that species becomes the exponent in the Kc expression. So if I had a 2 out front of that C, it would be C squared. If I had a 3 in front of the D, it would be D cubed. The coefficient becomes the exponent. we have that divided by the reactants, and note that we take the concentration of A raised to the power of that coefficient and concentration of B raised to the power of that coefficient. Note that when I write something like this, these brackets here mean concentration, specifically molarity. So writing something in the bracket like that implies I'm talking about the molarity. I can also write Kp. Kp is when I take the pressure in atmospheres of that species and raise it to that power of the coefficient. So we see here the coefficients become the exponents, but again, it is products over reactants. So the pressure of component C raised to the power of C times the pressure of component D raised to the power of D divided by the pressure of component A raised to the power of A times the pressure of component B raised to the power of B. And again, this is known, I most often call it your equilibrium constant expression or equilibrium constant, but you will hear law of mass action as well. This is the ratio though. This is going to help me determine how close am I to an equilibrium and where do my concentrations lie? Is this a product favored reaction? Is it a reactant favored reaction, or is it truly lying at an equilibrium? Because this relationship is comparing the amount of product I have to the amount of reactant I have. And it's giving me a ratio of those components, of those species. K is a capital K, not a lowercase k, and this K is called your equilibrium constant. A lowercase k is usually your rate constant. We're going to talk about that. We talked about that in your kinetics chapter, or you will talk about that in your kinetics chapter depending on when you cover kinetics. But this is a capital K. And we can also use K with many different subscripts. Each little subscript here represents a different type of K. Kc, concentration. Kp is for pressure. Ka is for acids. Kb is for bases. Kw is for water. Ksp stands for slightly soluble or solubility product. Let me write these so you can actually read them. I apologize. I forgot that I have a thicker font on right now. So Kc, C for concentration. P for pressure. A for acid. B for base. W for water. Sp for solubility product. This is for insoluble compounds or species. We told you in Gen Chem 1 that they're insoluble. Not quite true. Kind of exaggerated that a little bit. They're slightly soluble. How much? Depends on the KSP expression. Dis means dissociation, etc. You'll also see this written as KEQ. I tend to write KEQ, and I forget that the Tro textbook doesn't do KEQ because I learned it as KEQ. KEQ equals KC. So anytime you see me writing KEQ, I really mean KC for your base. It's the same thing. It means K at equilibrium. But the products, the concentration of the product raised to its coefficient divided by the concentration of the reactants raised to their coefficient as well. So for N2 gas plus 3 moles of H2 gas in equilibrium 2 moles of NH3, we always write it with the way the reaction is written. In this case, this is my product because the reaction is written with always reactants on the right or reactants on the left, products on the right. So we always write the K expression with the way we're writing the equation. So we see here, NH3 is my product. So for Kc, I'm looking at the concentration of NH3, and I've got a coefficient of 2 out here, so I'm going to raise that to the power of 2. I'm going to divide that by my products. I've got N2, and I don't have any coefficient on N2, so I'm not going to put any coefficient up here. And I also have H2, and the H2 has a coefficient of 3, so I'm going to raise that to the power of 3. That is my Kc expression. For Kp, that is the pressure in atmospheres. And again, remember these brackets mean molarity. For Kp, it's the pressure in atmospheres. So I've got the pressure of NH3, my product, squared because of that 2. I've got the pressure of N2 with nothing up here because there's no coefficient up front, and the pressure of H2 with that pressure cubed, and that is my Kp. You need to be able to write out these expressions. So please practice writing out some of these expressions and get comfortable with them because we're going to be using them a lot throughout this chapter and the next few chapters to follow.